So in this lesson, we're going to go ahead and start a discussion of multiplicative inverses for the integers modulo n. To motivate this, I want us to revisit one of the homework exercises regarding fill. So in one of the homework problems, you had the following. You needed to verify why Phil's argument was incorrect. Well, they almost always are wrong. But right now, I want us to consider the case when everything is just solving for x over the integers. So find x and z such that 2x plus 6 is equal to 4. What Phil did works over the integers because what he was really doing was multiplying both sides by 1/2. And so by doing this, Phil attained that this here was equal to x plus 3 is equal to 2, and then x is equal to -1. And so we have our solution over the integers, of course. But when we're working with the integers modulo 8, we need to be very careful. In the integers modulo 8, we have a complete set of representatives, 0, 1, all the way to 7 bar. But there are no fractions. Unlike the integers, there's no ambient space containing the integers modulo 8. We don't have fractions. So we have to be very careful in how we solve equations like this. So we cannot go ahead and multiply by 1/2. But what Phil was doing does work at times, because the property that we are employing is that 1/2 is the multiplicative inverse of 2, because if we multiply 1/2 times 2, we get back 1. So we could ask the following. Does 2 in Z8 have a multiplicative inverse? So that is, does there exist some number in Z8, so the integers modulo 8, such that 2 times x is equal to 1? And I leave it to you just to go through the motions and verify this. We can go through and say, okay, 2 times 1, that we get about 2. 2 times 2, 4. Then we get 2 times 3, 6. None of those are 1. And if you continue going all the way and exhausting the complete set of representatives from 0 to 7, we see that this is not the case. There is no x. And so the answer is no. And so we saw an example along these lines when we were looking at the multiplication table. Some numbers have multiplicative inverses modulo n, others don't. Had we instead switched the question from 2x plus 6 to say 3x plus 6 is equal to 4, and then now we're looking at, I want to do this modulo 8, then can we solve this? And the answer is yes in this case, because now if we look at 3 bar in the integers modulo 8, 3 bar times 3 bar is going to give us 9 bar. But 9 is congruent to 1 mod 8, so this is just 1 bar. And so, in effect, if we multiply both sides of this equation by 3 bar, and so I'm going to pass down to integers modulo 8. So actually, let me do this in two forms. One thing that we're going to be doing is working usually in this notation rather than in this notation. So I'm going to do this step in two ways. So first, modulo 8. So we have 3x plus 6 congruent to 4 mod 8. And then we're going to multiply both sides by 3. And so notice now we're multiplying. So we're working still with the integers. We're not looking at fractions as happened with the 1/2. And so doing so gives us 9x plus 3 times 6. We're going to have there 18. And then that this is going to be congruent to 12 mod 8. So we have this. So we can go ahead and subtract the 18. And we have the 9x is congruent to minus 6 mod 8. But now, let's look at 9. 9 is just 1 mod 8. And so we have, since 9x is congruent to x mod 8, the answer we want is x congruent to minus 6 mod 8. But minus 6 is the same as 2 mod 8. And so we have our answer. And so we can go ahead, verify. If we plug in 2 into x, we have 6. 6 plus 6, 12. And 12 is congruent to 4 mod 8. And so we are good. But working in the notation of congruence classes actually simplifies our steps. So now we're going to do the same exact question. We have 3x plus 6 congruent to 4 mod 8. So I'm going to write this as 3x plus 6 congruent to 4 mod 8. We know by the equivalent conditions for congruence that this is the same as 3 bar x plus 6 bar equals 4 bar. And now this is in the integers modulo 8. If we multiply both sides by 3, we get this. And so we have 9 bar x plus 18. So we're just doing the same exact things we did. But now with congruence classes, we just know already 9 is 1. So we just have 1 bar x. And so we can just now write the 1. We're looking at 18 modulo 8. That's going to be 2. And 12 is going to be 4. And so we get that the answer that we want is x equals 2 bar. And so we get the same response that we had working with the notation of congruence over here. And so oftentimes what we will be doing is using the bar notation. But the key thing I want to point out is we are interested in this lesson in finding when can we find a multiplicative inverse for a number modulo n. And so what conditions do we need? And so let us go ahead and get started. So we've been talking about multiplicative inverses, so let's go ahead and define this in generality. Because there's nothing special about working with the integers or the integers modulo n. We can actually talk about this for any ring. And in our case, the prototypical rings we're working with, integers modulo n, and later on in the course we're also going to be working with the Gaussian integers and some more general constructs. So whenever we have a ring, so just think integers modulo n, we say an element of that ring has a multiplicative inverse if we can find an element, which we're going to be writing as x inverse in R, such that x times x inverse is equal to 1. And we're going to call that x inverse the multiplicative inverse of x. Now, something to be mindful about. We are used from our earlier schooling to write R inverse to equal 1 over R. But we are not interpreting R inverse to be 1 over R. So we just saw that in the integers modulo 8, 3 times 3 is equal to 1. So in other words, the multiplicative inverse of 3 is itself. And that's how we will be interpreting these results for this course. As another example, we can go ahead and work in the integers modulo 5. Working over the integers modulo 5, we have that 2 times 3 is 6, so that's just going to give us back 1 bar. So we can use the notation for the integers modulo 5 that 2 inverse is equal to 3 bar. But again, the 2 bar inverse is not to be interpreted as a 1/2. However, it still has all those properties that we come to associate with 1/2 when working with the integers. And that's the key thing to keep in mind. That while we use this notation, it's not that we have fractions, but that the behavior that we expect of fractions when we multiply with an integer, 1/2 times 2 is 1, that property is preserved. Our motivating example showed us that 2 does not have a multiplicative inverse modulo 8. If we look at the integers modulo 6, we also have that 2 does not have a multiplicative inverse if you go by brute force. And even worse, 2 times 3 is the same as 2 times 0, which is 0. So we don't have a cancellation law. So we don't have that A times B equals 0 implies that A is equal to 0 or B is equal to 0. So we're not going to have this. When we work with the integers modulo 8, we also have that 2 bar times 4 bar is equal to 0 bar. And what we are going to see is that this failure of the 0 theorem that we have for the integers, A times B is 0, then 1 of A or B is 0, is actually intertwined with the property of having a multiplicative inverse. In the integers modulo 8, 2 nor 4 have multiplicative inverses. And we have that when we multiply them, we get back 0. So the first theorem actually is going to tell us exactly when we have a multiplicative inverse. So we're going to be working with so we have n is a natural number, a bar is a congruence class in the integers modulo n. And so the theorem says that a bar has a multiplicative inverse precisely when the GCD of a and n is 1. So in other words, a and n are both relatively prime. So let's prove this. So we're going to do the forward direction first. So assume that a bar in the integers modulo n has a multiplicative inverse. So by definition, there exists some number, let's go ahead and call it x in the integers, such that if we take the product of a bar times the congruence class of that integer x, so a bar times x bar, we get back 1. So we have this equation, and now we have to make an observation. Most of the theorems we have for GCD, and specifically the conclusion, we have the GCD of a and n is 1. So we want to go over back to the realm of the integers. And so we're going to apply one of the equivalent conditions from last time of what it means to have a congruence modulo n. And so this is equivalent to the following, to the existence of an integer k such that ax is equal to 1 plus kn. And so here we have our statement, and so this is just coming from the equivalent conditions we proved last time for the integers modulo n. So we know that ax is equal to 1 plus k times n. And now what we are going to do is subtract the kn to both sides. So then we have that ax minus kn is equal to 1. But what does this remind us of? We have a linear Diophantine equation. And what we have is that x and k are a solution. So specifically, we have that if we let x comma y be x and k, then is a solution to the linear Diophantine equation ax, actually let me make this minus just to be in line with the notation we've been using, plus ny is equal to 1. But this has a solution if and only if the GCD of A and N divides 1. And so this is one of the things we prove for solutions to linear Diophantine equations. But the GCD is a positive integer. Well, specifically A and N are not 0, so we have in this case that the GCD of A and N is 1. And so that shows the forward direction. Let's do the converse to the backwards direction. So now, assume the GCD of A and N is 1. By Bézout's lemma, there exists integers little x and y such that ax plus ny is equal to 1. Now, this equation, if we reduce modulo n, yields the following. So now I'm gonna use the bar notation. So we're descending down to the integers modulo n. But n, the congruence class of n, is 0. So we have that this here is a bar, x bar is equal to 1. And so therefore, a bar has a multiplicative inverse, namely x. So therefore, x bar is, let me just write a notation that we just established. X bar is the inverse of A. And so now this is using the notation from the definition. And so x bar is the multiplicative inverse for A, and we are done. We have now proven the theorem, and we can now see that the reason that 2 did not have a multiplicative inverse modulo 8. So in Z8, 2 bar is not a multiplicative inverse, does not have a multiplicative inverse. Since the GCD of 2 and 8, of course, is not 1. But namely, in this case, it's 2. And so that concludes it for the theorem. And we now have a way of checking when we have multiplicative inverses. Because the way that we approached it in the introductory example today was just, let's go by brute force. 2 times 1, 2 times 2, 2 times 3, 2 times 4, and then we can see we never get back 1. But that's not efficient as our n grows large. But now we know exactly how to deduce when we have a multiplicative inverse modulo n. So the previous theorem tells us that the integers modulo n has much more structure than what we are accustomed to with the integers. When we work with the integers, we know that 2 does not have a multiplicative inverse as an integer. Of course, 1/2 is a multiplicative inverse, but that is a rational number that is not an integer. But with the integers modulo n, we have seen that working over the integers modulo 8, 3 bar is a multiplicative inverse, is its own multiplicative inverse, and the previous theorem tells us how to determine whether a given element has a multiplicative inverse. And so I want us to move on now to the notion of a field. This is a fancy word for things that we are already accustomed to. You have worked with the rational numbers, the real numbers. If you have taken a course in complex analysis, you have also worked with the complex numbers. These are all examples of fields. And the defining property of a field is that every non-zero element has a multiplicative inverse. So the precise definition is the following. If we start with a ring R, we say that a ring is a field if every single non-zero element x in that ring has a multiplicative inverse. So in other words, we can find some x inverse in that ring such that x times x inverse is equal to 1. And when we work with the integers modulo n, it turns out that in some cases, the integers modulo n is a field. In other words, we have all the properties that we are used to with the real numbers, the rational numbers, but now it's a finite set. And that's what this corollary is going to get at. We have p as a prime number, then the integers modulo that prime is a field. The converse to this statement is also true, but this is going to be left for homework, specifically exercise number 10 of 8.3. But we will go ahead and prove this corollary. Before proving it, I want us to recall the following statement. So let D and N be natural numbers. We know that if D divides N, then D is less than or equal to N. The contrapositive to this statement is the following. So we have to negate D is less than or equal to N. If we negate that, that means D is greater than N, and that implies the negation of D divides N. So in other words, D does not divide N. So let's now prove this. So by definition, the integers modulo p is the set of congruence classes 0, 1 bar all the way to p minus 1 bar. This is a complete set of representatives for the integers modulo p. Now let us go ahead and take an element a bar in the integers modulo p. So let a bar be in the integers modulo p, and we can suppose further that one moment, I want to take a non-zero element. So I'm going to look at the integers modulo p, but remove 0. And so this is what I am doing here. I am removing 0 from that set. And so I want to go ahead and consider that a, as an integer, is between 1 and p minus 1, and we have that the inequalities are also allowed for equality. And so we have this here. Then we have that p is greater than a. And now by the contrapositive, so this statement over here, we have that p does not divide a. But then, since p is prime, we have that the GCD of a and p is 1, since p is prime. And so we have that but now a was an arbitrary non-zero element in the integers modulo p. So now by the theorem, so by the previous theorem, a bar has a multiplicative inverse in ZP, and therefore ZP is a field, and we are done. So again, we started off by assuming that A was an arbitrary non-zero element in the integers modulo P. So moving on, let us now prove what is known as the modular cancellation law. And so this is what Phil in the homework exercise failed to ensure. He used the modular cancellation law by multiplying by 1/2, but that's not allowed in the integers modulo 8. But now we actually have a way of canceling. So specifically, we have n is a natural number, a bar, x bar, y bar. These are all congruence classes in the integers modulo n, and we have that the GCD of A and N is 1, so they're relatively prime. And we want to prove that if A bar times X bar equals A bar times Y bar, then we get back X bar equals Y bar. Now the proof just follows from the fact that we know that GCD of A and N is equal to 1. So by the theorem, we have that GCD of AN equals 1 implies that there exists some A bar inverse in the integers modulo n such that A bar inverse times A bar is equal to 1 bar. Now, we get that if we start with A bar times X bar equals A bar times Y bar, from the lesson from Friday, we know that we can multiply both sides of this equation by A inverse, so A bar inverse. And so we have this equation. But because A bar inverse and A bar are multiplicative inverses, we just get back that this is going to be 1 bar, so we get back X bar. Oops, I forgot the X bar there. So X bar is equal to Y bar. And that's it. We are done. We have proven our result by doing this. So let us go on and restate the modular cancellation law. And this is something to be mindful. Right now we just proved it, but we were using the language of congruence classes. But we know that the language of congruence classes is equivalent to the mod notation. And so, said differently, we have that theorem 8.3.2 in the textbook is the same as theorem 8.3.3. Namely, the same assumptions, just no more congruence classes. Now n is a natural number as before, but now ax and y are integers with GCD of a and n being 1. And if ax is congruent to ay modulo n, then x is congruent to y mod n. And so that's just going to be a restatement. And in the same manner, we can now state Euclid's lemma, well, the original Euclid's lemma. The book, as a reminder, refers to Euclid's lemma as a stronger statement. But if we consider the original Euclid's lemma, we have that if p is a prime number and we're looking at the integers modulo p, and we have x bar, y bar in the integers modulo p, and if the product is equal to 0 bar, then x bar is equal to 0 bar or y bar is equal to 0 bar. So let's prove this. So proof. So if x bar is equal to 0 bar, then the statement holds, of course. So suppose that x bar is not equal to 0 bar. But if x bar is not equal to 0 bar, we know that the integers modulo p for p a prime number is a field. So since the integers modulo p is a field, there exists some multiplicative inverse in the integers modulo p such that the multiplicative inverse of x times x bar is equal to 1 bar. So now we look at our equation. When we look at x bar times y bar is equal to 0 bar, we multiply both sides by the multiplicative inverse of x. And so we have this here. But now x inverse times x is going to give us back 1 bar, so we're going to get back a y bar here equals a 0 bar. But that's just y bar is equal to 0 bar, and we are done. We have now proven the modular Euclid's lemma. And so something just to be on the lookout, and this is something just to emphasize the build-up of everything we have done. We have proven Euclid's lemma in an easy fashion, but we want to be mindful that when we work with the integers modulo n, we have already packed into everything the ingredients that originally went into proving the original Euclid's lemma. If we go back to our proof, of the theorem, which we just used by virtue of quoting that the integers modulo P is a field, then this proof relied on Bezout's lemma, which is the main ingredient for Euclid's lemma. And so even though we have a different proof of it, specifically a different proof of Euclid's lemma in this realm of modular arithmetic, it really is the same proof, just that we are now translating everything into modular arithmetic. And that's one thing we're going to be seeing as we go on. We're going to be continue to translate some of the statements we did before into this language. So next, we are going to move on to what is known today as Wilson's theorem. But before getting to the theorem itself, I want us to rediscover the statement. And let's go ahead and do this in the footsteps of mathematician Ibn al-Haytham in the 11th century. And so what I want you to do is to consider the following setup and find a pattern. So let's go ahead and suppose that P is a prime number, that P be a prime number, and without proof, this is just a numerical investigation, then I'm going to put this in blank, this is what I want you to fill in, is a factor of 1 plus P minus 1 factorial. So what I want you to do now, and feel free to use Wolfram Alpha, a calculator, go ahead and consider the following. So write the factors down for P, and then specifically for 1 plus P minus 1 quantity factorial. And so write down the prime factorization of this quantity for some primes. And so we can go 2, 3, 5, 7, and let's see if we find a nice pattern here. So now that you have gone ahead and done a couple of examples, let's go ahead and see what we've got. If we look at 1 plus P minus 1 quantity factorial, if we look at P equals to 2, well, we just get back 2, and then for 3 we get back 3. But once we get to 5, we get 5 squared, and then we get to 7, we have a 7 as a factor. We look at 11, also a factor, and then 13 is also a factor. So this led al-Haytham to conjecture the following: that if P is prime, then P divides 1 plus P minus 1 quantity factorial. Now, al-Haytham did not claim to have proven this. He just based it off numerical evidence, could not prove it, and said so. Unlike our friend Pierre de Fermat, had he discovered this through numerical investigation, would have probably written a marginal note saying, I have discovered a marvelous proof of this, which this margin is too small to contain. And the proof of this actually eluded mathematicians all the way until 1771, when Joseph Louis Lagrange was finally able to prove this result. Today we are actually going to do a proof of this, but using the language of modular arithmetic, which Gauss introduced and simplifies Lagrange's argument tremendously. But it should be worth noting that Wilson's theorem, as is known today, is at the foundation of what is known as group theory. And so group theory, we've been talking about rings, integers modulo n. A group is much more general. With a ring, we have addition and multiplication. With a group, one only focuses on one binary operation. So you can look at a set with addition, a set with multiplication. With functions, you can look at a set with composition of functions as an operation between the elements. And so these are things that are studied in abstract algebra at length. And the techniques that go into proving Wilson's theorem are at the backbone of the foundations of group theory. So why is it called Wilson's theorem? And so in 1770, Edward Waring published an article that stated this statement as a theorem. And in the statement said that his student, Wilson, had a proof of this. Later, several months later, they published a retraction that was an incorrect statement. Apparently, Wilson had come upon this statement that P divides 1 plus P minus 1 quantity factorial through numerical investigation but did not have a proof. But that article eventually fell in the weeks following the publication into the lap of Lagrange. And Lagrange sought to prove this result and succeeded. And so we are not going to be proving it in the way that Lagrange did, but as I mentioned, in the way that Gauss did using modular arithmetic. And so what we are going to do is rephrase this. We have a statement about divisibility. If we want to rewrite this in the language of congruence, what we are saying is that 1 plus p minus 1 quantity factorial is congruent to 0 mod p. But if we subtract the 1 over, what we are saying is that p minus 1 factorial is congruent to negative 1 mod p. So if we prove this congruence, we prove Al-Haytham's observation. We are done, and then that's where we're going to head towards. And to do so, we're going to go ahead and talk a bit more about multiplicative inverses, as that is the backbone of the proof. So our first step towards Wilson's theorem is to revisit the example we did at the start. We already saw that in the integers modulo 8, 3 bar is its own multiplicative inverse. So we now want to consider the case when we are working over the integers modulo 8 prime. And we want to ask, when do we have that an element is its own multiplicative inverse? And the answer is that we only have 1 bar and p minus 1 bar. So specifically, p is prime. If x bar is its own multiplicative inverse, then x is either 1 or p minus 1. So how does this proof go? So we have that x bar is its own multiplicative inverse. So if x bar in ZP is its own multiplicative inverse, then by definition, this means that x bar times x bar, which is x bar squared, is equal to 1 bar. But if we subtract on both sides by 1, we get x bar squared minus 1 bar is equal to 0 bar. We factor, that's a difference of squares, so we have x bar plus 1 bar times x bar minus 1 bar is equal to 0 bar. But the integers modulo p is a field, and we prove that we have a cancellation law. Specifically, we have already shown that if this is equal to 0, we have x bar plus 1 bar is equal to 0 bar, or x bar minus 1 bar is equal to 0 bar. And so this tells us that x bar is either negative 1 bar or x bar is equal to 1 bar. And we have part of the statement. For the second part of the statement, observe that p minus 1 is congruent to negative 1 mod p. And so therefore, p minus 1 bar is equal to minus 1 bar, which finishes the proof of this lemma. And now we are ready to prove Wilson's theorem. So let us go ahead and now prove Wilson's theorem. We're going to be using a lemma, which is actually part of your homework assignment. So this is in 8.3, number 9. And so what it says is, if n is a natural number, then if a bar is in the integers modulo n has a multiplicative inverse, then its multiplicative inverse is unique. And so we're going to be assuming this as part of our proof. And so with that, let us go ahead and get started. So we want to prove that p minus 1 factorial its congruence class is the same as the congruence class of negative 1. And we have already seen that if we prove this, we show that p divides 1 plus p minus 1 factorial. So how do we do this? We're going to break it into two cases. So first, let p equal 2. So if we let p equals to 2, then we have 2 minus 1 factorial, which is just going to be 1 factorial, which is just 1. But 1, if we're looking at modulo 2, that's the same as negative 1. So 1 is going to be congruent to negative 1 mod 2. And so we have this, so we are done. And so now we consider the rest of the primes. So now suppose p is greater than 2, and a corny joke, because p equals to 2 sometimes it's isolated in this way, we call it the oddest prime. Drum roll. Okay, so corny jokes aside, we have p is greater than 2, so we have an odd prime. So p is an odd prime. And now what we are going to do is consider the list of numbers 2 bar, 3 bar, all the way to p minus 2 bar. So consider the list. Two bar, 3 bar, comma, 3 bar, all the way to p minus 2 bar. Then this list has p minus 3 elements. And let's go ahead and just let this be m. So since p is odd, m is even, so that's just the number of elements in the list, 2, 3, all the way to p minus 2. By lemma 8.3.8 that we just proved, so by lemma 8.3.8, none of the elements in the list, and so by this list here, is its own multiplicative inverse. So we have that each of these elements is not its own multiplicative inverse, but we also know, because we're working over the integers modulo p, that they all have a multiplicative inverse. So since P is a field and they are non-zero elements, each element in star has a multiplicative inverse. And now by the lemma, which you will be proving for homework, we have that each of those multiplicative inverses are unique. So by lemma, this is the homework exercise 8.3, number 9. The multiplicative inverses are unique. Now, what we are going to do is rearrange the list in star. So now, in star as the following. We're going to start off with A1 bar, and we can choose A1 bar to be 2 bar. And then the next element in the list is going to be A1 inverse. And so we're going to go ahead, rewrite, find its inverse, and then put it right next to it. So now that's how we're writing our new list. Then the next element will be A2 bar. And so the way we choose A2 is as follows. If 3 is the multiplicative inverse of 2, then A2 would be chosen to be 4. If A1 inverse is not 3, then we choose A2 bar to be 3 bar. And so in this way, we can go ahead and continue adding elements to the list until we exhaust everything. But doing so here we have an A2 inverse bar. Doing so means that we're going to get all the way to m over 2. There's going to be we're going to stop at m over 2 bar, and then its inverse. And so I know that this may be a bit hard to read. This is a subscript m over 2, and then its inverse over here. And so this list is exactly the same as the list we have up here. But why are we doing this? Why are we rearranging it in this way? Well, the reason is that now we're going to take a product. So we're going to consider the product 2 bar times 3 bar all the way to p minus 2 bar. So we have this here. All right. But now every element appearing in this product is the same as all the elements appearing in this list that we rearranged with this notation. So now we have that this here is the same as A1 bar times A1 inverse times A2 bar times its inverse, all the way until we get to AM over 2 bar times its inverse. But each of these is 1. A1 times A1 inverse, 1. A2 times A2 inverse, 1. A sub m over 2 times its inverse, 1. So the whole product is 1. So we have 1 bar. Now if we look at p minus 1 factorial, we end up getting that this is 1 times 2 times 3 to p minus 2 bar times p minus 1 bar. But we know that the inner term, 2 all the way to p minus 2, that's 1. So we are left with 1 times p minus 1. But now p minus 1, so this 1 times p minus 1 bar is just p minus 1 bar, but p minus 1 bar is the same as minus 1. And that concludes the proof. We have now proven Wilson's theorem. And so we're done. So to finish this off, we're going to go ahead and consider the following theorem due to Gauss. Now, one thing I wanted to say before we move on is something that I mentioned earlier, that Wilson's theorem is intertwined with the foundations of abstract algebra. And one thing that we will see in the lesson for next Monday is that Wilson's theorem, along with this result of Gauss that we're about to prove, are used in proving Fermat's Little theorem. And so we'll talk about this in more detail later. And so these are two results we're going to come back to and build upon. The other thing is that in the process of Lagrange proving Wilson's theorem, he proved a more general statement about polynomials, which we will cover later in this course, and it is that statement that is known today as Lagrange's theorem in abstract algebra for those of you who have taken it. But as we will see, it bears little resemblance with the statement that is covered in an abstract algebra course, because that is due to Camille Jordan in 1861. And so one of the things that we will see as we go through the course is how all these statements we're going to be continuing to build upon. And so here we're proving this statement of Gauss, but in a couple of lessons we are going to be generalizing this even further. So let's go ahead and get started. With Gauss's theorem, at least this Gauss theorem, what it says is, if we're looking at a natural number n and take a bar to be an element in the integers modulo n, and consider the list a bar times 0 bar, a bar times 1 bar, and then just multiply it by every single element in the integers modulo n, then every element of the integers modulo n occurs exactly once if and only if the GCD of a and n is 1. Said differently, what we are saying is, because the integers modulo n we know that this set can be written as those elements A bar such that 0 is less than or equal to A, less than or equal to n minus 1. So what we are saying is that we have another way of writing the integers modulo n if A and n are relatively prime, specifically as the set A bar times n bar, where now we let n bar go between 0 and n minus 1. So how do we prove this? So one direction is easy. So let's do the easy direction. So this is the case where we assume that the list contains every element exactly once. So I'm going to go ahead and call that list star. So suppose star contains every element of the integers modulo n exactly once. Then that means that there must be some x in the integers modulo n such that A bar times x bar is equal to 1. Because if we contain every element from 1 through n minus 1, from 0 all the way to n minus 1, we can then find some x. So we have this here. But if that's the case, then x bar is a multiplicative inverse to 1. So then A bar has a multiplicative inverse in the integers modulo n. By the theorem on multiplicative inverses, so by earlier theorem, this happens exactly. So this is equivalent to the GCD of A and n being equal to 1. And so now that takes care of one direction. And so now we are left to prove the converse. So let us go ahead and do that now. So for the converse, let us suppose that the GCD of A and n is equal to 1. Now, what we want to do is prove that if this is the case, then this list is the same. So in other words, that this set is equal to the integers modulo n. So let's go ahead and call this set here S. So it suffices to show that S is equal to the integers modulo n. And what we are going to do now is prove this by double inclusion. So we're going to choose an element in S and show that that element is in the integers modulo n, and then prove the converse. And that will show equality for the two sets. So one direction is automatic. So namely, if x bar is an S, then by definition, x bar is equal to A bar times m bar for some m bar in the integers modulo n. But the integers modulo n is a ring, and A bar is in the integers modulo n. So in particular, we have that x bar is in the integers modulo n, and so we have that S is contained in the integers modulo n. And so now we want to show the converse. And so conversely, let's go ahead and take a element B to be in the integers modulo n. By assumption, so our assumption is that A and n are relatively prime. So that tells us that there is a multiplicative inverse for A in the integers modulo n, such that a bar times a inverse is equal to 1. And so here we're using the theorem. So theorem on multiplicative inverses. And so we have this here. And so now what we are going to do is the following clever trick. So we're going to take y bar to equal the inverse of a, and then multiply that times our element b. And once we do this, we're going to go ahead and multiply a times y. So then, a bar y is equal to a bar inverse b bar, which is equal to b bar. And so we have this here. But we are done. Because what we have shown is that we can find an element y bar in the integers modulo n, such that y bar times a bar gives us that b bar. So thus, a bar y bar, which is equal to b bar, is an s. And so we have that s is the integers modulo n is a subset of s. Consequently, since we already showed the opposite direction, s is equal to the integers modulo n, which concludes the proof. And so we got it. And so that concludes it for today's lesson. And so the next lesson is going to have us go into further detail about the integers modulo n with what is known as the Chinese remainder theorem. And then this coming Monday, then we are going to go into generalizations of this theorem and also applying Wilson's theorem to get Fermat's little theorem, which Fermat did not prove.